The purpose of this lab was to analyze position data obtained from a system moving about its surroundings, and then using this information to determine the forces acting on it. In the experiment, the system was a star rotating around a black hole, and recorded data points of the star's location were used and imported into VPython. After importing the data points, we were able to use our knowledge of Newton's second law and the universal law of gravitation to obtain the mass of the black hole, as well as the forces acting on the star. The only force assumed to be exerted on the star was the force of gravity from the black hole, making this F net. And further calculation gave us the black hole's mass of 3.7812 times 10 to the 31 kilograms. The data used as the star's position throughout its motion was obtained from a spreadsheet containing all of its points at each time step. In this observation, the time step was 86,400 seconds, or 1 day. Compared to the total duration of the time the star moves, this time step is small, so it will work well in our calculations and in the model. First, the mass of the star had to be specified. This was a known value. The time step, delta t, was also specified, and we had to identify that the time at which the program starts is at 0 seconds. The recorded positions of the star were imported as shown here. This data was used to calculate the velocities between each point. The velocity can be calculated from the position data by taking the final position minus the initial position, all divided by the change in time. This procedure can be repeated at each new position. This is where using VPython comes in handy. Python finds the velocities between each location using this information. The momentum of the star is then able to be calculated from the corresponding velocities. By multiplying the change in velocity times the mass of the star, change in momentum can be obtained. Knowing the change in momentum brings us very close to finding the net force acting on the star at the given time. Taking the change in momentum divided by the change in time yields what we call dp dt. Newton's second law tells us that the change in momentum over the change in time for the star has an equivalent value to the force of gravity that the black hole is exerting on the star. Since gravity is the only force we assume to be acting on the star, this is the net force on the system. After all the star's positions are taken down and the net forces are calculated, Python gives us this model of the star rotating around the black hole. The arrows represent the net force in yellow, the parallel component of the net force in black, and the perpendicular component of the net force in blue. The direction of the arrows represent the direction of the corresponding force at each point of the star's positions. As can be seen from the model, the perpendicular component of the net force always points perpendicular to the object's motion, while the parallel component points in the direction of the object's motion. This makes the net force equal to the sum of the two components as it was specified in our code. We now have all the data needed to solve for an unknown, which is the mass of the black hole. To find the mass of the black hole, we rearranged the law of universal gravitation and solved. This equation yielded a mass of 3.7812 times 10 to the 31 kilograms. While the net force and its components have an equal value to those of dp dt and its corresponding components, it does not make these two principles the same. Calculation tells us that the change in momentum over the change in time is equal to the net force, but it is important to note that the change in momentum over the change in time is not a force. dp dt is the effect of the net force. We know from the momentum principle that if the net force is zero, the change in momentum is zero. So this allows us to understand that the change in momentum over the change in time can only be non-zero if the net force is non-zero. The net force, in this case, is the cause of dp dt, and the two are completely separate principles. The fact that they have equivalent values is just a coincidence of the universe. So now we can ask the question, what if we replace the black hole with another black hole in the same position? Given the same position data and assuming gravity is once again the only force acting on the star, would we be able to tell a difference in the new black hole's mass? The answer to this question is no. Since the star remains in the same orbit, the mass of the new black hole would be calculated in the same way. The constant g would remain the same, r would be the same, and the mass of the star is the same. F net, since it was calculated from the star's position, will be the same as before too. So solving for this new black hole's mass, as we did before, will give us the same value. So in conclusion, we were able to find forces acting on an object starting from observations. After identifying the system, we were able to work backwards and use observations to find the net force acting on it from our knowledge of Newton's second law. Then, we specified what interactions contributed to the net force so we could solve for the unknowns, which in this case was the mass of the black hole. Thank you.